Hi students, I'm back with a session on sound for class 8 CBSE and ICSE students, and this particular presentation is coming from Navayug study channel. It is Navayug study channel, and if you want to actually access the videos of Navayug study channel, you can definitely go to the YouTube, or it is youtube.com/Navayug study, or you can also go to this website navayugstudy.wordpress.com. This is our website where you find all the videos for various classes. And this is our email ID, navayug.study@gmail.com. If you have any questions or queries or anything and you want to interact with us, please use this email ID. And there are also ways of submitting questions and asking for a Google Plus video conference session for clearing doubts if required through this website, navayugstudy.wordpress.com. And we also have a Google Plus community. It is plus.google.com/plus Navayug study. Okay, fine. So let us get into the session on sound. Now, I don't want to ask you the question, what is sound? You're going to kind of look at me and say, what are you asking? I mean, anybody knows what sound is, right? Yeah, that's true. But what you're going to learn in this session is the physics of sound. How does the sound work? How does the sound get transmitted? What are the various characteristics of sound, like the wavelength, frequency, right? What do you mean by high-pitched sound versus low-pitched sound? What do you mean by a loud sound versus soft sound?
What do you mean by musical sound and noise?
Yeah, so what do you mean by musical sound and what do you mean by noise? So there are all these various aspects of sound that we're going to study in this session. And to begin with, we're going to look at what produces sound, right? What produces sound? Now, it's a very trivial question when it looks to be a trivial question, but definitely it needs some reasoning on what produces sound. And in fact, the sound is produced by vibration. Now, what do you mean by that? Now, a simple example is when you talk, you just hold your finger here. Yeah. So just hold the hand when you talk near the throat, right? And you can see that there's something which is vibrating, right? That is what is called the vocal cord. There's something called a vocal cord inside in this area, the throat area, and that vocal cord is vibrating, and that vibration is what actually is producing sound. And that's how you're able to talk, you're able to sing, you're able to shout, and do whatever, right? So there is vibration. Now I want to show you a few other examples of how the sound gets produced. Now here we are going to look at a couple of experiments which actually shows that sound is being produced because of vibration, right? Now, so a vibrating tuning fork. Now, a tuning fork is in fact
It is a U-shaped fork. When you hit it on something, it makes a sonorous sound.
Yeah, so the tuning fork is a U-shaped fork, and when you hit it, it produces a sound with a certain frequency. It's a apparatus which is used in labs for doing a lot of tests related to sound. And what you see in this video right now is actually a tuning fork, right? And once you hit it, it starts vibrating. So this is a tuning fork, and what is really happening is that this is vibrating this way. It's vibrating to and fro this way, and that vibration is what is actually producing the sound. Now what this experiment is proving is that the tuning fork is indeed vibrating. Right? Now, since it's vibrating at a very high speed, the naked eye may not be able to see it. So to prove that it is vibrating, what they have done is they have just put they have got a light ball, right, suspended on a thread, and it is kept near the tuning fork. Now see what really happens, right? As the tuning fork is vibrating, the tuning fork is vibrating, and because of the vibration it is hitting. So as it is vibrating to and fro, when it is moving this way, it is hitting the ball, and because of that the ball is moving away. Right? So this proves that the tuning fork is indeed vibrating. Right? Because if it doesn't vibrate, if it doesn't have a motion, it actually it will not be hitting the ball, and the ball will not move. Right? Yeah, tell me, students. Okay, so this is proving the fact that the tuning fork is vibrating. Now, so this actually is a simple experiment which proves that the sound is produced because of vibration. I want to show you another example, right? I want to show you another example here. This is actually a violin, right? Now this is a violin. These are strings of violin, and this is what we call the bow of the violin. So this is a bow of the violin, and these are the strings. Now what you can see is when he's bowing, what is really happening is the string starts vibrating. Right? So let us look at that. When he bows, this is shown in slow motion, right? So the motions of the bow is, you can see, is very slow, and you can see the strings vibrating. Don't you see that? So here you can see as the bow is vibrating, bow is moving. You can see the bow is moving, and in fact bow is moving very fast, but this is shot in slow motion, and you can see the string is vibrating, right? And it is because of the vibration of the string the sound is produced, right? So you can see the vibration of the string, and in fact that string will be vibrating in a certain frequency, and that is the frequency of the sound which it produces, right? Now, so again, you can see here the sound is being produced because of vibration, right? Did you see that? So another example. Now let us look at this. Now this is basically a symbol, right, of a drum, which produces pretty loud sound, kind of a sound when you hit it, right? Now let us see what really is happening when you're hitting. You can see that the symbol is vibrating, right? So you can see that slowly it's again shot at a slow motion, and you can see what is happening. It's bending and is vibrating, right? It's vibrating, and that vibration is what is producing sound. You can see it is vibrating pretty heavily, and that vibration is what is producing sound, right? So from all this you can see that the vibration is a key source for creating sound. Without that there is no sound, right? So that is what I actually want to tell you, and these examples are really proving that fact. And I also told you can hold on to your throat here, touch the throat and start talking, and you can see there, you can feel the vibration, and that vibration is of the vocal cord, which is there inside near the throat, which is really producing the and there are muscles, in the throat area, which kind of allows the vocal cord to vibrate in different frequencies, and that is how you are able to produce sound of different frequencies. For example, if you look at You can see I am able to produce sound with two different frequencies, and that is why one was a little kind of a bass kind of sound, and the other one was more like a higher pitched sound. That is because the same vocal cord, because of the muscles which are around, I am able to change, using those muscles, you are able to make the vocal cord vibrate in two different frequencies, and that is how you are able to produce the sound with different frequencies. And that's how you are able to sing. Otherwise, the humans can only produce sound with one frequency, which is not okay. So nature has given you such a beautiful thing called vocal cord, which allows you to make sound with different frequencies, and that's how you're able to sing. All right, so these videos, I hope, have made you understand that any sound, vibration is required. Without vibration, there's no sound, right? So any sound source vibrates to produce sound. All right, so oops. Okay, sorry for that. So now I want to just tell you what is a tuning fork, right? Tuning fork is an apparatus which is used very often, right, in laboratories, and in fact in this session again and again we'll be looking at tuning fork, because tuning fork is something which we'll use for all the sound related experiment. So this is what a tuning fork is, right? Now it is a U-shaped bar which is typically made of steel, right? So it's a U-shaped bar made of steel, and every tuning fork, a specific tuning fork, vibrates in a specific frequency, right? So I can change the thickness of this, and there are certain things which I can change based on which the frequency in which it vibrates changes. So different tuning forks will vibrate with different frequencies, right? And so this is what a tuning fork is. I hope that's clear, right? And so let me go back here. So what is a tuning fork? Tuning fork is a U-shaped steel fork with steel handle. Two arms of the tuning fork. Just a moment. So the two arms, that's the two arms of the tuning fork, is called the prongs, and then the handle is called the stem. So if you go back here, so these are called the prongs, and this is the stem, right? So it has got the two prongs and one stem, and stem is where you hold it. Now typically for vibrating, what you do is you take the tuning fork and then just hit the prong, one of the prongs, on a table or wherever, and then it starts vibrating, producing sound with a specific frequency, right? So that's basically what a tuning fork is. All right, okay, fine. So I think two things are clear. One is the sound is produced always because of vibration, and we also seen what a tuning fork is. Okay, all right. Now let us get into oscillatory motion. In fact, in 7th standard physics, in a time and motion chapter, I have discussed what is oscillatory motion.
It is also like kinematics.
Yes, so it is definitely related to kinematics, and oscillatory motion is something which I have discussed there, but we'll just revise it once again if at all any of you have not gone through that, or just as a refresher. So what is oscillatory motion? Oscillatory motion is it's a to and fro motion of a pendulum about its mean position is called oscillation, right? So if you look at this pendulum, and you can see this is a oscillatory motion, right? So you have the to and fro motion of the pendulum. Don't bother about those vectors v and a. They basically are showing the velocity vector and the acceleration vector of the bob as it moves this way and that way, but that's something that you're not discussed yet, right? So don't worry about that. But you can see it's a to and fro motion. The bob is actually having a this is basically the bob, right? and this is a bob, and it has got a to and fro motion, right? So it's got a to and fro motion about the mean position. This is the mean position. That is where the bob will come to rest. So the rest position of the bob is the mean position, right? And this to and fro motion about the mean position, and that is what is oscillatory motion. In fact, the pendulum is one example, but there are several other examples that can be given, right? So oscillatory motion, but one of the examples is a simple pendulum. Okay. So now there are a few terminologies which is related to the oscillatory motion, and that's what I want to talk about here. Right? So now the terminologies is, this is actually called the amplitude. So that is a maximum displacement the bob has from its mean position. That is the amplitude, right? So maximum displacement the bob has from its mean position. So this is the mean position, right? And what is the maximum displacement the bob has from the mean position while it is oscillating? That is its amplitude. Okay. And what is the frequency? Frequency is the number of oscillations per second. So how many times it moves to and fro about the mean position every second is its frequency, right? And what is a period? Period is the amount of time taken for one complete oscillation. One complete oscillation, correct. So what's the time taken for one complete oscillation? That is what is the period, right? So let's just go back here. Oops. So amplitude is a maximum displacement of the bob from the mean position. Frequency is the number of oscillations per second, and period is the time required for one complete oscillation, right? So these are actually some of the terminologies that you remember when you talk about oscillatory motion. All right, now let us go back and look at tuning fork, right? Now in the case of tuning fork, again, what you can see is I just want to quickly show you just a moment. Okay, fine. So if you look at the tuning fork, as I told you, the tuning fork also, the prongs of the tuning fork vibrate, right? I want to actually, let me see whether I can show you that, just a moment. You can see what is happening with tuning fork. Again, yeah, I just want to show you. This is actually shown in slow motion, right? And you can see that what is happening to the prongs. The prongs are vibrating. And what kind of motion is this? Yeah, actually it is moving very fast, but this is in slow motion. Yeah, it is oscillatory motion. You can see it is oscillatory motion, and you can see what is really going on, right? If you, yeah. So this is the main position, right? And what is happening is that it is going this way. Oops. Let me oops, let me use a line. Yeah, so it's going that way, right, and then it's going this way, right? So it is oscillating. And what's the mean position? This is the mean position, right? So that's a mean position, and it is oscillating about the mean position, so it's an oscillatory motion, which means it has got an amplitude, it has got a frequency, and it has got a period, right? And so, and that oscillatory motion is what is producing the sound. Is it clear? Okay. So, so what I am discussing about is about when the tuning fork is struck, prongs of the tuning fork oscillate or vibrate. As I showed you in the slow motion in that video, it is really oscillating. The prongs are oscillating, right? Maximum displacement of vibrating body from its mean position is its amplitude. So that's something which I told. So if you look at the prong, how much is the maximum for, if you look at, go back to the video, right, and look at this. Oops. So what is the maximum displacement this prong has from its mean position, right, in the to and fro motion? No, so can't be told, but that's basically what amplitude is, right? Now, if the tuning fork is struck harder, then what happens?
Then the amplitude is more.
Amplitude will be higher. So the prongs will start vibrating more, right? And which lead to a higher amplitude vibration. Just a moment. Okay, so it leads to a higher amplitude vibration. Larger the amplitude, more is the loudness. Now, what is loudness? Right? Loudness is the volume of sound, right? So when you say loudness, what you mean is the volume of sound. For example, so the second one is louder than the first sound, right? So loudness is related to the volume of sound. And what happens is when the amplitude of vibration increases, the loudness or the volume is increasing. If you look at a speakers, right? If you look at the speakers, you can find that as the volume increases, there's a diaphragm in the speaker. I don't know. Have you observed there's a circular diaphragm in the speaker, and it kind of vibrates, right? And that's what produces the sound, right? We'll be looking at how a speaker works later on. Don't worry about that. We'll be covering it. Now, and you can see when the volume is increased, it starts vibrating even more with a higher amplitude, right? So when there is more amplitude, there is more loudness or more volume in the sound, right? Even when you look at this vocal cord, you can see you compare, you can see when you are having a higher volume, you can feel the vibration more because there's higher amplitude of vibration. Loudness is proportional to square of the amplitude. So what does that really mean, right? So let us go back and see what that means. So loudness is proportional to, as you know, this is how ratio and proportions, right? Square of the amplitude. So assume amplitude is A squared, which basically means that if A is amplitude, A stands for A is amplitude, and L is loudness. Right? So which means that assume that amplitude doubles. So assume the amplitude doubles, which means from A it becomes 2A. Then what will happen to the loudness? It will become
twice the volume than it is before.
No. which means you're saying L will become 2L. Is that true? L is proportional to square of the amplitude. So when L is proportional to square of the amplitude, when the amplitude becomes 2 twice, then what will happen to L? L is proportional to square of the amplitude, means 2A squared, right? So which basically means the loudness will become 4 times, right? Ratio and proportion, something which you have learned in mathematics. See, you should not say that I have learned something in mathematics, I will only use it in mathematics. I will not use it anywhere else. That should not be the way. What you have learned in mathematics is a general principle. It can be used in economics, it can be used in physics, it can be used in chemistry, it can be used in wherever. Doesn't matter. Right? Statistics, wherever. The concept of ratio and proportion is something, if you have understood well, you can use it in anywhere. So here, we are saying that loudness is proportional to square of amplitude, right? Which basically means when the amplitude becomes twice, the loudness becomes 4 times. Yes. Right? So that's basically what it means. Right? Is this clear? Is this clear? Huh. So assume amplitude becomes 3 times, loudness will become 9 times, right? That is basically what happens. Okay? Right. So that is basically what it is. So loudness is proportional to square of the amplitude, right? And loudness is measured in what you call decibels. Now, just for the time being, think that it is measured in decibels. It is what you call the the reason why I'm not explaining about it is because it is basically a logarithmic scale, and you have not learned what is a logarithm, right? Yes, yet you have not learned about logarithms. So without understanding logarithms, it's difficult for me to explain what is decibel, how the decimal scale works, right? But just understand that the unit of loudness is decibels. Okay, that's all what you have to understand. I'm not explaining the unit as usually I do. I explain Newton, I explain meter per second, Newton per meter squared. I explain the units, but here I'm not able to, because you should know what is logarithm for understanding that, and that's something that you learn later on. Okay, so that is about oscillations. We have seen that tuning fork prongs oscillate. We have looked at the loudness is dependent on the amplitude of vibration, right? And it is proportional to square of the amplitude. So when the amplitude becomes 2 times, the loudness becomes 4 times, right? But when the amplitude becomes half, what happens to the loudness? It becomes 1/4, right? So that is basically what happens, and that is the dependency between amplitude and loudness. And loudness is nothing but the volume of the sound being produced. So one aspect, so that is one characteristic of sound. One characteristic of sound is how loud is it. The other characteristic of sound is what is its frequency, right? The different variety of sounds. You see, oh, that's a shrill sound. Why do you say that? Oh, his sound is so shrill, because it is in a higher frequency. Whereas, oh, he has got a very bass sound, because that sound is low frequency, right? So you are able to see there are so many different variety of sounds, and that variety of sounds is because of the difference in their frequencies. There is a difference in frequency between the male and the female, right? The male has got so there is a difference in frequency between the males and the females, right? So you can see that. So that's what. So there are variety of sounds, and that variety is because of difference in frequency, right? So now what is frequency? Frequency is number of vibrations per second, right? So how many vibrations the vibrating body has per second is its frequency, and it is measured in what you call hertz, right? Now, now how did you get, now the hertz is named after somebody. It is, yeah, Heinrich Rudolf Hertz. He's a German physicist produced radio waves of ultra high frequency with help of rapidly oscillating electric spark. He called them electromagnetic waves. You know, I want to just give you one associated information, right, which probably a lot of you may not know. Now, who invented radio waves? Who invented Mercury? No, Marie Curie is not radio waves. Marie Curie is the person who invented radiation, right? Radiation. What do you call a gamma radiation because of the atomic fission. So that's not what it is. So everybody says Marconi invented radio waves. So Marconi. Yes, but it is not Marconi. It is actually the J.C. Bose. Sir J.C. Bose was the first person who demonstrated radio waves, and that was the beginning of knowing electromagnetic waves. And that kind of kicked off so many other inventions. But sadly, nobody talks about Sir J.C. Bose. But we are all Indians. We should acknowledge him. He demonstrated radio waves for the first time, and he had a thesis paper on which was published about radio waves and its characteristics. Right? So yeah. So a lot of people say that radio waves are invented by Marconi, but that's not right. It was invented by J.C. Bose before Marconi, and I just wanted to tell, since we talked about waves and frequency and amplitude and all that, I just thought of just giving this associated information, right? All right. Now, so Hertz is named after Heinrich Rudolf Hertz, right? Who did research in the electromagnetic waves area, and in memory of him, the frequencies unit has been given as Hertz, right? Now, how does the frequency influence the kind of sound? So when you look at a low frequency versus a high frequency, right, what is the difference? So I just want to show you the difference between that, right? Just what do you mean by the low frequency versus high frequency? How does the sound wave look like, right? That's what I want to show you. How does a sound wave look like, right? What is the characteristic of the sound wave, right? Now, if you look at this, right, this is an instrument called trombone, right? And we are going to look. It's like a trumpet. It's a musical instrument, trombone, right? Trombone, yeah. Now we want to look at how. So now what are these? What are these graphs here, right? Yes, they are the frequency graphs. It's called the frequency spectrum.
The graphs will show frequency upon frequency.
Yes, frequency spectrum. So it kind of shows. So when you look at instruments like trumpet, flute, and all that, right? That sound which is produced actually is multiple frequencies. It's not just one single frequency. So you can see here. You can see here that this is a frequency spectrum, and on the x-axis you have the frequencies, right? On the x-axis you can see these are frequencies. Oops. And y-axis it is actually the decibel, which is, can say, strength. Yeah, strength of for every frequency. So what this really means is that the sound which is being produced, it got highest strength for frequencies around 0.5 hertz, right? So here is where the peak is there, right? So 0.5 hertz, so it has got a higher strength, but the sound wave also has some few other frequencies like 2 hertz, 1 hertz and all that, but that strength is lower. So the strength of the 0.5 hertz is higher, so which basically means that it is a low frequency sound which is being produced. Whereas you look at the here, you can see the peak is somewhere here, right? Peak is somewhere here around 1.5 hertz. So which basically means that this sound is of a higher frequency than this sound, because here the peak is at 0.5 hertz, here the peak is at 1.5 hertz, right? So that is, so by looking at the frequency spectrum, you can kind of see what are the kind of frequencies in that sound wave.
So
This spectrum is so how is this frequency spectrum produced? What happens is that the sound wave is digitized, right? There's a way of digitizing the sound wave, and that digitized sound wave goes through what we call Fourier. Huh?
what is
Digitized sound wave means, so the sound wave can go through certain things where the sound wave is converted into digital data, right? By using concept of sampling. Right now, that'll get into signal processing, right? We cannot go lot of detail into that, but what basically it means is that the sound wave, which is what we call so if you typically look at a sound wave, it is converted into data form, right, by digitizing it, and that digitized data is converted into a frequency spectrum by using what we call fast Fourier transform, right? FFT. There are different types. There's discrete cosine transform, fast Fourier transform. There are different ways, right? So these are all mathematical models, big time algorithms which are used for producing this. Don't worry about all these names. I'm just telling that there are a lot of complex things which happens to produce this kind of a frequency spectrum, right? So tell me.
so those two are different frequency spectrums for high pitch sound and low pitch sound.
Yeah, so now let us look at this. Let us run this, right? Let us play this sound. You saw that? There's a variation.
That's a high pitch sound.
Yeah, so that is what. So if you look at, if you go back and look at this thing, initially it was a low frequency sound.
So that's the low.
That becomes high frequency. So you can see initially it started in low frequency, and then it is going to high frequency. Saw that? And you can see how the spectrum is changing.
So you're saying the low frequency was changing into
High
high frequency.
frequency, right? So the sound which is produced initially is low frequency sound, and that is what the spectrum shows here too, right? And then it changes to a higher frequency, and that is what the spectrum shows here. So that is the influence of frequency on the type of sound, right? And that's what you say, oh, one is high pitch, the other is low pitch. When you look at a high pitch sound and do a spectral analysis, you can see that its peak will be at a higher frequency, right? So that is basically what it is. Is it clear? Any questions? Clear? Okay. So frequency of vibration is low, means it is a low pitch, or you can say, usually you say it's a bass or bass.
Or a deep sound.
Yeah, if you are a Western musician, you have a bass guitar. You know, as a bass guitar, typically the bass guitar,
Low frequency sound.
it produces low frequency sound. The bass, that's why it's called bass guitar, right? And the bass. So if you look at the your audio systems, you will have something called bass. One one knob will be available called bass. Why is that there? When you increase it, you're saying, okay, I am going to increase the loudness of the low frequency part of the sound being produced. For example, if it's a song which is being played, right? So in that song, there could be instruments which has got low frequency, right? And there could be instruments which has got higher frequency. When I am increasing the bass knob, when you are turning it to maximum, what you're trying to do is you're trying to increase the relative loudness of the low frequency instruments. That's what you're doing, right? So bass is, understand, see, why I am telling you all this is because understand, relate things to your life, day-to-day life, right? You're learning physics for that. You're not learning physics for just scoring some marks in an exam. You should be able to explain things around you. Why is that bass knob there? When I am rotating it, what is happening?
Because the low frequency sound is something.
No, it is not like, so the explanation is not something to do with low frequency. No. What we are doing is when you're increasing the bass, you're saying that, so in your, no, the music which is being played, there could be instruments which is producing sound of lower frequency. You are increasing the loudness of those instruments. So you're increasing the loudness of the low frequency part of the sound in that song. That's what you're doing, right? Now, frequency of vibration when it becomes high, you say it's high pitch, shrill, right? Like a whistle, right? If you look at a whistle, that whistle sound, right? It's usually shrill. You feel that it penetrates into your ear.
Like even sometimes in Western music, some singers shout, that is also shrill.
Somebody shouts doesn't mean it's shrill. It could be a bass sound, but at very high loudness.
No, sometimes when some.
So the example, a very good example of a high pitch sound is a whistle, right? So if you look at a whistle is very shrill, right? Now, usually, now the reason why a whistle is, why is whistle used? Whistle is used for people to notice, right? A police person blows a whistle. Why? To kind of get attention from people.
Even small children, when they scream, it's very shrill.
Yeah, when they scream, it's true. Yeah. Now, why the police uses whistle is because
So that the person hears.
it's a high pitched sound, and typically the high pitched sound travels for a larger distance. So you will hear it even if you are far, right?
Suppose if you're on the topmost floor of a building, then also you can hear it.
Yeah. So that's what. So the frequency. So you understood the low frequency, high frequency, and I explained using the frequency spectrum. I showed you how the frequency spectrum looks like for that trombone, right?
Play the sound also.
Correct. Okay. Is it clear? Okay, fine. Voice of a child is shriller than that of an adult. Of course, so when I was a child, when I was 5 years old, my sound was shriller. Then what happens is, usually for boys around teenage, some changes happen to the vocal cord, and the frequency starts. Yeah, the frequency they produce starts becoming lower, so less shriller, right? Okay, now when we say frequency of a tuning fork is 256 hertz, it means that it vibrates 256 times per second, right? So if you look at, I don't know whether you've seen a tuning fork. I'm sure that you should ask your teacher to show you a tuning fork. And usually each tuning fork, on that, it will be written how many hertz. Which basically says that if I hit the tuning fork somewhere, it will vibrate at that frequency. And the sound which is produced will be of that frequency. Right? That is basically what it means. You understood? So, and when it says that the frequency is 550 hertz, which means that the prongs vibrate 550 times per second. And that is why you're not able to see it with the naked eye. Right? Because it's so fast, it is vibrating so fast that your eye is not able to detect it. And that is where you may have to, so that's why I showed you a video in slow motion where you could see the prongs vibrating, right? And it is because we've used a slow motion camera, you were able to actually see that. Okay? Clear? Any questions? All right. So I will just discuss about the period and then how the period is associated to frequency, and with that we'll stop the session for today, right? And we'll continue later on. So what's a period? So period is the amount of time required for one oscillation or one complete vibration, one complete cycle of vibration about the mean position, right? And now what is the let us look at what is the unit of frequency. Yeah, hertz. What does hertz mean? It is times per second, right? Or you can say number of oscillations per second. Now what is period? Period is time taken for, so let us say this is, usually frequency is denoted by F and period is denoted by capital T, right? So time taken for one oscillation. Perfect. Now can I associate period to frequency? If I know the frequency, can I find the period? So if you look at what is this, this is the time taken for one oscillation. This says in 1 second how many oscillations. So if I do 1 by F, right, what are you getting? Second by oscillation. Or let me explain it in a little more better way. Oh, shucks. Okay, came back. All right. Now, let's remove this. All right. So, see, the frequency is saying that in 1 second I have so many oscillations. Right? If I do 1 by frequency, what am I getting? I'm getting the time required for one oscillation. Right? Which is nothing but is equal to T. So 1 by F is equal to T. So this is an important relationship. So somebody says that the frequency of the tuning fork is 500. I can find the period. What is the period? T is equal to 1 by 500, which will be 1 by 5, 1 by 5 is what? 0.2, right? So 0.002 seconds. That's a period, right? So that's basically what it is. So if I know the frequency, I can find the period. If I know the period, I can find the frequency also. Huh? Because it's a frequency. Frequency is 500 hertz. What's the period? 1 by F. 1 by 500 is 0.002.
How?
You divide and see. Divide and see.
Yeah, fine.
So now, as the same way, if given a period, the frequency is again same thing. F is equal to 1 by t, right? Linear equations. I multiply F here, right? So I can divide T here. So I would divide T here, multiply F here, multiply F here. So same thing, right? So if I am known the frequency, I can find the period. If I have the period, I can find the frequency. Okay? Clear? All right. So with this, we will stop the session, right, for the time being, and we'll continue continue with sound in the next session. Before I stop, I want to just once again let you know that this video is coming from Navayug Study, right? Please access our website navayugstudy.wordpress.com. The YouTube channel is youtube.com/navayugstudy. And if you want to send any emails to us, it's navayug.study@gmail.com. Bye-bye. Have a great day and see you soon for the next session of sound. Till then, enjoy your life and study well. Bye-bye.